Very good morning, students.
Good morning.
Good morning, sir.
Good morning, all of you. Let us start with the discussion. Last class, we have been compared about the plus M effect order of OH and OR. We said that oxygen in OR is more electronegative than oxygen in OH. So OH will be a better electron donating group. Yes or no? That is plus M effect. Compare NH to OH, NH C double bond O R, O C double bond R. So if you think carefully, you will be getting NH2 will be greater because NH nitrogen is less electronegative. Because of less electronegative nature, it can't withhold the electron density on nitrogen greatly. But oxygen is more electronegative, it can withhold the electron density greatly. So nitrogen will be a better electron donor by the plus M effects, and then oxygen. Among NH2 and OH, you can compare like this. But after that, you have NHC double bond or OC double bond or NHC double bond or OC double bond or nitrogen has lone pair of electrons. That lone pair of electrons on nitrogen will be in resonance with the pi electron density of oxygen. This oxygen's lone pair is also in resonance with the pi electron density of oxygen. So when you try to compare these two, the net electron donation from nitrogen will be less because it has been resonance with the adjacent C double bond O. So that is why NHC double bond R will be greatest, then OC double bond R. Again, if you try to compare these two, since the nitrogen is less electronegative, it can have more donation when compared to oxygen. So this will be the complete right order. Is that clear or not?
Yes.
Yes, sir.
That's right. So then come mesomeric effect. Summary of mesomeric effect and inductive effect also. Mesomeric is dominating when compared to inductive. Atom or group directly attached to conjugate system has a lone pair or negative charge. That means this scenario. Atom or group directly attached. Either it has a lone pair or it should be having a negative charge. Negative charge on the group can also be in resonance with the pi electron density. Lone pair present on the group that can also be in the resonance with the pi electron density. So in that case, you will be having plus M effect. Minus M effect means atom or group directly connected that should be having a positive charge, or it should also be having a conjugated double bond system like A double bond B, which is again polar. Electronegative difference should be there between A and B. In that case, you can have electron density moving away. So it is these two cases will be coming under minus M groups. Plus M means atom or group directly attached to conjugate system and has lone pair or negative charge. Minus M means atom or group directly attached to conjugate system has polar pi bond or positive charge or vacant orbital or positive charge or vacant orbital. These are the cases of your plus M and minus M effects. And let us look at different groups. NH2. NH2 will show what type of order? Plus M, plus I, minus I. Plus
Plus
M,
M and
minus
minus
plus M and minus I.
minus
Yes,
M.
or plus M because it has lone pair of electron, minus I because it holds, it will directly withdraw the electron density because nitrogen is more electronegative when compared to the carbon. OH will also have same effect or not? OH
Yes.
plus M
Yes, sir.
and minus I. NO2. NO2 will have what effects?
Minus M and minus I.
Minus M because N double bond O system is there. So we can take phenyl group N double bond O. Yes or no? So in this case, pi electron density comes into the N double bond of pi electron density moves away. So it is electron withdrawing by resonance. So minus M. It is also electron withdrawing by inductive effect minus I. CHO will also have the same order. The C double bond of pi electron density moves away. Yes or no? C double bond of pi electron density moves away, and it is also withdrawing the electron density. It is also withdrawing the electron density because of minus I. Why? Because C double bond of carbon, that C double bond of group is there, right? C double bond of group, it is connected with some alkyl group, let us say. This carbon has some partial positive charge. Because of that partial positive, it withholds the or withdraws the electron density. CH3 will have what effect?
Plus I only.
Plus I effect. Hyperconjugation is not involved. We'll discuss about hyperconjugation. Then we can say alkyl groups also involved in the hyperconjugation. NH3 plus. NH3 plus, it will not have any resonating structure because lone pair of electrons and nitrogen are not present. It will only have minus I. O minus, negative charge on oxygen, and also it is more electronegative when compared to carbon. Negative charge on oxygen. Oxygen is more electronegative when compared to carbon, but look at this order. RO minus. Oxygen, although it is more electronegative, will it withhold the electron in C? Understand this point carefully. If it attracts the electron in C, what happens? The O minus is already having negative charge. If it attracts the electron in C, negative repulsion will be increased. Because of that, system becomes destabilized or stabilized.
Destabilized.
Destabilized. So system wants to get stabilized, so it will release the electron in C. It is not just a OH. If that is just an oxygen, in that case, due to electronegative difference, the electron in C moves towards oxygen. But O minus, already oxygen has negative charge, so it can't withhold, it can't withdraw the electron in C by inductive effect because of repulsions. So it will be donating electron, donating O minus. Same concept you can apply to C double bond O minus. Look at this. C double bond O minus. If you try to connect this to particular phenyl group, what will happen? If you try to connect that to particular phenyl group, it will withdraw the electron density by resonance, so minus M. And now it is connected to some alkyl group C double bond O minus. Now can I say R C double bond O minus as R C oxygen O oxygen, and between these two oxygen atoms the pi electron density is moving, and we have a negative charge here. Can I say this C double bond O minus is carboxylate is having a negative charge? Because of the negative charge in this particular carboxylate, it can't withdraw the electron density. If it withdraws the electron density, negative repulsions will be high. So ultimately, the net electron density is actually donated. Because of that, stability is gained. So it is also a plus I group. C double bond O minus is also a plus I group and minus M group. Similarly, O C double bond O plus M because lone pair of electrons are there, and minus I because oxygen is directly connected because it withholds. C double bond O same minus M because electron density is going to be like phenyl group is connected with a C double bond OR. So pi electron density moves into C double bond pi electron density moves away. And we can also say inductive effect R C double bond OR means this pi electron density is moving towards oxygen. Carbon has partial positive charge, so it withdraws the electron density. So minus M and minus I. Similarly, C triple bond and minus M minus I, CO minus M plus I, C double bond OH minus M minus I. Fluorine is having plus M, and it is also having minus I. Is that clear, students? Whenever the atom or group contains lone pair of electrons or negative charge, it will be electron donating group by mesomeric effect, that is plus M group. If it is withdrawing the electron density, the atom or group should contain positive charge or a double bond, polar pi bonded system. So that is how we can actually understand about mesomeric effects and inductive effects in combination. The next kind of effect we can think of is hyperconjugation. Hyperconjugation means what? Complete transfer of electrons of CH sigma bond towards a positive charge or free radical or pi bond. Towards the positive charge or free radical or pi bond, if the CH electron density is actually going to be completely shifted, then that is said to be hyperconjugative effect. So what is that? It is also known as no bond resonance or Baker-Nathan effect. So how that hyperconjugation can be understood, we'll look at now. So what actually happens is, whenever we have a carbocation or alkene or free radical, in that case hyperconjugation is present. For carbon ions, there is no hyperconjugation. The complete transfer of CH sigma electron density into the adjacent positively charged carbon, that is vacant orbital carbon, or free radical or C double bond system, that is said to be your hyperconjugation. Let us look at this hyperconjugation or no bond resonance for different cases and write the respective hyperconjugated structures. Hyperconjugation in carbocation. Let us take a carbocation like CH3 CH2 plus. Now look at this carbocation CH3 CH2 plus and understand how the electron movement is happening. CH3 CH2 plus. Can I say this carbon which has positive charge, that is going to withdraw the electron density of carbon-carbon bond or not? Yes or no? Because
Yes,
this carbon has positive charge, it will withdraw the electron density. Because of withdrawing of electron density, this carbon gets what charge? Delta plus charge. Because of this delta positive charge, what happened to the CH electron density? That is also moving towards carbon. And this CH electron density, which is actually moving, because of this moving, hydrogen develops partial positive charge. Now, can I say, whatever the sigma electron density we have here, that has a tendency to penetrate into the adjacent vacant p orbital. The sigma electron density tries to penetrate into the adjacent vacant p orbital. So ultimately, what we can say is, this CH sigma electron density comes into, that means this CH electron density comes into, and you will form a double bond with the CH2 because this p orbital is involved now. So HCH double bond CH2, and this carbon hydrogen bond is going to be cleaved now. There is no bond between carbon and H plus. Why it is H plus? Because electron density is lost from hydrogen. That is why H plus. Carbon hydrogen bond is not present, so no bond resonance. CH3 CH2 plus and CH2 double bond CH2 H plus. These are nothing but hyperconjugated structures. Can I say we have one more hydrogen here? Like two more hydrogens are there. Those two hydrogens can also involve in the similar type of resonance. So H plus CH2 double bond CH2. Also we can have H plus CH2 double bond CH2. So these are nothing but your hyperconjugative structures. Hyperconjugative structures. So more number of alpha hydrogens, more will be the number of hyperconjugative structures or not? Yes or no?
Yes.
More number of alpha hydrogen, means more number of hyperconjugative structures. Hyperconjugative structures. Greater the number of hyperconjugative structures, greater will be the stability. More will be the stability. So if you have hyperconjugate difference in the number of hyperconjugative structures, then that's resonating structure which has more number of hyperconjugative structures, that is more stable. Conditions. What are the conditions you have? Alpha carbon. The alpha carbon is a carbon which is directly connected to the carbon of carbon bearing positive charge. Alpha carbon should be sp3 hybridized. Alpha carbon should not be involved in double bonded system. Alpha hydrogen must be present. Alpha carbon should be sp3 hybridized. It should have hydrogen. And how many resonating structures we will be having? So number of hyperconjugated structures is equal to number of alpha hydrogens plus 1, because 3 alpha hydrogens are there. So 3 structures plus this one. So 4 hyperconjugate structures you will get. Number of alpha hydrogens plus 1 will be number of hyperconjugate structures. You don't need to go with that. You can simply say greater the number of alpha hydrogens, greater will be the stability. Greater the number of alpha hydrogens, greater will be the stability. So compare the stability now. CH3 C plus CH3 CH3 C6 H H11 plus, and we have CH3 CH3 plus. Among these two, which is going to be more stable among these three? CH3 C plus CH3 CH3 has how many alpha hydrogens?
9.
9 alpha hydrogens. Here we have how many alpha hydrogens?
11 or 4.
2 to 4 alpha hydrogens. Here we have any alpha hydrogens?
No. 0, sir.
0 alpha hydrogens. So greater number of alpha hydrogens, greater will be the stability. So 9 alpha hydrogens more stable, then 4 alpha hydrogens, then 0 alpha hydrogens. Note, number of hyperconjugated structures is directly proportional to number of alpha hydrogens. So that will be proportional to stability. Yeah, Arshia, any doubts? Just a second. Okay, right. So this is how your hyperconjugation will be. CH3 CH2 plus. Look at the CH sigma electron density, how is it moving? The CH sigma electron density is actually now shared between the p orbital, empty p orbital of carbon, forming the pi bond. So CH2 double bond CH2 and CH plus is formed. Look at the structure, how it is changed. Initially we have sp3 hybridization for the carbon atom. This carbon atom is sp3 hybridized alpha carbon, so it has tetrahedral shape. But now look at, as soon as the double bond is formed, it has to become a trigonal planar. So the planarity has maintained. The planarity was maintained and H plus ion is present here. H plus ion will be present here. It is also known as no bond resonance or Baker-Norton effect. Compare stability of carbocation directly proportional to number of alpha hydrogens, because that will be directly proportional to hyperconjugate effect. Compare the stability between these three. So first one has 9 alpha hydrogen, second compound has 6 alpha hydrogen,
6.
third compound has 3 alpha hydrogens. So A, B, C, that will be the order of stability.
A greater than B greater than.
A greater than, B greater than C. Very good. Nine alpha hydrogens, 6 alpha hydrogens, and 3 alpha hydrogens. A greater than, B greater than C. If alpha hydrogens is more, then positive charge is dispersed on more hydrogens, so stability will be more. So positive charge, why you can ask a question, sir, why more number of alpha hydrogen means more number of hyperconjugated structures. So why should be more stable? Because whenever the charge is present only on one atom, then it is going to be attracted by oppositely charged species easily. But if the same charge is distributed over many atoms, then the charge distribution is high, means obviously stability is gained. Right? So answer A greater than, B greater than C. Hyperconjugation free radical. In the carbocation, in the carbocation, in the free radical, in the carbon-carbon double bond, we can have hyperconjugation, not in carbanions. Free radical also same scenario. What happens now? What happens now? You will be having, whenever CH bond is there, you have to cleave this bond in such a way, such that one electron you have to give to hydrogen, the other electron you have to give to carbon. So this one electron on carbon and one electron on the CH2 dot, they will pair up to form CH2 double bond CH2 and H dots. And again that will have H dot CH2 double bond CH2. With all the 3 hydrogens, 3 alpha hydrogens, we have the same scenario. So conditions, again same condition, alpha carbon must be sp3 hybridized, alpha hydrogen must be present. Alpha carbon must be sp3 hybridized, alpha hydrogen should be present. Try to compare here. Order of stability, which is more stable? Among these two, which is more stable? In the first free radical, how many alpha hydrogens are there? CH2 dot is connected to carbon, which is not connected to any hydrogen, so 0 alpha
9.
hydrogens. In the second one, 9 or 0?
0.
0, right? Because it is alpha carbon do not have any hydrogens. Whatever the second molecule, 3, this is alpha,
7
this is
alpha
alpha, this is
hydrogens.
alpha. 7 alpha hydrogens. So more stability, more number of alpha hydrogens, more will be the stability. Stability of carbon free radical is directly proportional to hyperconjugate effect, which is directly proportional to number of alpha hydrogens. CH3 C dot CH3, CH3 CH dot CH3, CH3 CH2 dot. Same again, 9 alpha hydrogens,
9.
6 alpha hydrogens, 3 alpha hydrogens. Based on the number of alpha hydrogens, we can compare the stability, right? Very good. Hyperconjugation in alkenes. In alkene also we have same system, like we have CH2, CH3, CH double bond CH2. I can say the CH electron density comes into the C double bond C pi electron density moves away. So if you try to write the stability or the hyperconjugated structure in alkene, so you'll have this type of structure. This is the hyperconjugative resonance structure. The CH electron density will be donated to the next carbon-carbon bond. The carbon-carbon pi electron density will be moved to away. That means we will be generating a carbanion system. So you get a HCH and a CH plus will not have any bond. Carbon-carbon double bond, C double bond CH, CH2 minus. Like that we have 3 hydrogens. So we will be having 3 more structures. 3 alpha hydrogens. So this is your carbon-carbon double bond system now. This is the alpha carbon. For the free radical, to the free radical carbon which is directly attached, that is alpha carbon. To the positively charged carbon, which carbon is directly attached, that is your alpha carbon. To the carbon-carbon double bond system, which carbon is directly attached, that is nothing but your alpha carbon. To the C double bond system, the carbon directly attached is alpha carbon. This alpha carbon has 3 hydrogens. So more number of alpha hydrogens, more will be stability. Again, same condition. Alpha carbon must be sp3 hybridized. Alpha hydrogen must be present. Same conditions. Alpha carbon should be sp3 hybridized. Alpha hydrogen should be present. Compare here, which is more stable? CH3, C double bond C. This is your system. C double bond system.
6 alpha hydrogens.
6 alpha hydrogens here. You can take this double bond system. If you take this double bond system, what you will be having?
7.
You will have This is alpha, this is alpha, this is alpha.
7.
So what you will be having? 3 plus 2 plus 2, 7 alpha hydrogens. But is it stable or less stable?
Less stable.
Because of repulsion, it is going to be less stable, because if you look at the free radical is present on sp2 hybridized carbon atom. Yes or no? With respect to this free radical, we have what? How many alpha hydrogens? With respect to this free radical, we have
3.
with respect to this free radical, we can have, this is not sp3 hybridized, this is sp2 hybridized, this is sp2 hybridized, only 5 alpha hydrogen
5
with respect to
free radical.
free radical. Okay, sp2 hybridized vinyl free radical is unstable due to repulsions. So this is stable. Note, hyperconjugative effect involves delocalization of both sigma and pi electrons. Okay, both sigma and pi electron, because CH electrons which were involved, they were actually the sigma electrons, and the pi electrons of alkene, they were also affected. Or in the carbocation or free radical, you are having a pi bond formation. So hyperconjugation effect involves both sigma and pi electrons. Stability of alkene again directly proportional to number of hyperconjugated structure, that is directly proportional to number of alpha hydrogens. Hyperconjugation is observed in carbocation, carbon free radical and alkene, and not in carbanion, because there is no tendency for the carbanion to accept the electron, because already octet is satisfied. Because carbanion has no vacant orbital. Carbanion has no vacant orbital, and it already has a negative charge. So vacant orbital not there, and the electron density is also not subsequently moving away from the carbon of carbanion, so it will not accept the electrons anymore. So obviously carbanion, it cannot accept the CH electron density, so no possibility of alpha hydrogens. It is not possible. No hyperconjugation. Stability of carbocation directly proportional number of alpha hydrogens. Stability of carbon free radical directly proportional number of alpha hydrogens. Stability of alkene also directly proportional to number of alpha hydrogens. These are the 3 points which you have to think of carefully. And with this logic, we'll solve the examples after just looking this reverse hyperconjugation. What is reverse hyperconjugation? Like when also have scenario like where CCl3 is connected, electron density is moving away. The CH electron density is moved away from the hydrogen. But if you have carbon-chlorine bond, chlorine is more electronegative. In that case, the chlorine has a tendency to pick the electron density. So this C double bond CC pi electron density comes into. So in that case, what happens? CH2 will have positive charge, C double bond C, Cl. Now the Cl will have negative charge. Earlier we have written, whenever we have CH bond, the CH electron density comes into the carbon-carbon double bond, pi electron density moves away. But now the carbon-carbon pi electron density comes into, the CCl electron density is taken to chlorine, because chlorine is more electronegative. So it is nothing but reverse hyperconjugation. CCl3 has minus H effect. Minus H effect means reverse hyperconjugation. In the case of minus H effect, electron density is taken away by that particular atom. CH2 double bond CH3 will be having reverse hyperconjugation. Reverse hyperconjugation or minus H effect in alkene. Right, students? Plus H effect on benzene ring. Where is the plus H effect will be present on benzene ring? Look at this scenario carefully. Try to write the resonating structure with respect to hyperconjugation. So we have this type of structure, CH3, and I am taking one of the hydrogen. The CH electron density comes into the carbon-carbon pi electron density moves away towards another carbon atom. In that case, you will be getting these two double bonds as it is. Negative charge will be present here. This C double bond C, CH2 will be present in this fashion, and CH2 and H plus no bond residence. Negative charge again comes into pi electron density moves away. You will have this type of resonating structure. Negative charge present here, double bond, CH2, H plus. Yes or no? Again, you will be having resonating structures like this. Negative charge comes into pi electron density moving away, negative charge at ortho, double bond positions, double bond CH2 and H plus. Ultimately, we have negative charge coming into pi electron density moving away to form this type of structure. double bond, double bond, double bond, and CH3. So this is how you can try to draw the hyperconjugative structures of your respective toluene. For toluene, you cannot only say that CH3 is electron donating group by inductive effect, it is also having hyperconjugative effect. And where is the hyperconjugative effect operative? It is operative at ortho and para positions only, similar to your mesomeric effect. Hyperconjugation is also operative at ortho and para. Alkyl groups directly attached to benzene ring increase the electron density in the ring through hyperconjugation. Alkyl groups are directly attached to benzene ring increase the electron density in the ring through hyperconjugation. Electron density increase at ortho and para. I have written the resonating structure. You can see at ortho and at para you will be having negative charge. So whenever we have toluene also, CH3 is an electron donor group or electron donating group. CH3 is electron donating group by inductive effect plus I group as well as by hyperconjugation, that is plus H effect. Because of hyperconjugation, electron density increased at ortho and para positions. So if you try to do the electrophilic substitution reactions of toluene, it will be ortho para positions occupied. The ortho and para positions are going to be attached by the electrophile. So if you look at a benzene connected to CHCl3, it is minus H effect, right? CHCl3 is minus H effect. Similar to minus M effect showing groups, deactivating group, electron density decreases at ortho and para. Meta director directs the incoming electrophile at meta position. How the resonating structures can be written here? Let us understand. So we have a structure like this: CCl2Cl, CCl. CCl3 have written as CCl2Cl. The carbon-carbon electron density moves away. This carbon-chlorine bond will be given to chlorine. So if you try to draw the resonating structure, you will get a double bond at these two positions as it is. C double bond C, CCl2, and you will have chlorine with a minus charge and a positive charge at ortho position. So you will have next resonating structure, pi electron density moving away, double bond position here, para positive, double bond CCl2, and here we have Cl plus. Again, subsequently move the pi electron density. You have positive charge at ortho. Double bond positions will be present in this fashion. CCl2 and Cl with a negative charge. Finally, you have what? Negative charge on chlorine coming into, pi electron density coming again back, generating CHCl3, Cl3. Carbon-carbon single bond, CC, and that carbon should be connected with 3 chlorines. So if you try to write the hyperconjugative structures, minus H, reverse hyperconjugation or minus H effect on benzene ring with respect to CCl3, you will be generating positive charge at ortho and para. If you have positive charge at ortho and para, when compared to ortho and para, the neutral position meta is electron rich or not? Yes or no? So electron density decreased at ortho and para means electron density at meta is high. If electron density at meta is high, the incoming electrophile is going to be substituted at meta position. So meta director group CCl3 will be a meta directing group. Understood now, everyone?
Yes.
Yes.
Yes, right. Hyperconjugation is distance independent because these are because of resonance structures. Because of resonance means hyperconjugated resonating structures. It is a permanent effect. It is not because of the presence of some molecule. It is because of the presence of movement of sigma CH electron densities. Generally, it is more dominant than inductive effect, but less dominant than mesomeric. So order is mesomeric greater. Mesomeric has greater effect than hyperconjugation, then inductive effect. We have some exceptions. The exceptions we have already discussed. Like halogens is the exceptional case. Inductive effect, if you compare CD3 greater than CH3, inductive effect means I have to look off electron donating tendency. I have explained with the concept of reduced mass also. CT3 is a better electron donating group than CD3 than CH3. But if you want to compare the hyperconjugation, what is the order? Like if I have CH2 plus, like given the example, look at this example, CH2 plus CH3, CH2 plus CD3. Here, if you try to write the hyperconjugated structure, CH2 plus CH3, the CH bond is a stronger bond or a weaker bond?
Weaker bond.
Weaker bond. So CH bond is a weaker bond means hyperconjugation is more easy in CH bond. That is, that bond can be broken easily. Two CH bonds can be present easily. H plus will be there. But CD bond, if you try to write, CD bond electron density comes into CH2 double bond C, two CD bonds and D plus. So CD bond is stronger bond. CD bond is stronger bond means that cannot be broken easily. So this is more stable based on bond strength. Because CH bond is a weaker bond, that weaker bond can be broken easily such that you can generate the hyperconjugated structure easily. So whenever you have a CD bond that cannot be broken easily, so hyperconjugation in CH2 plus CD3 is poor. But if you think of electron donation tendency by just inductive effect, CD3 is a better electron donating group when compared to which is a better electron donating group? CD3 is a better electron donating group when compared to CH3. But hyperconjugated effect will be reverse. CH3 greater, then CD3, then CT3. Understand these cases carefully. Hyperconjugation is different, exactly opposite to that of inductive effect, because in hyperconjugation the CH bonds have to be broken. Right? Stability of alkene directly proportional to number of alpha hydrogen, that is directly proportional to number of hyperconjugated structures. Compare the stability of these two alkenes, CH3, C double bond C, CH3, CH3, CH3. Like first example you can take A and B, which is more stable? The compound A has how many alpha hydrogens? This is carbon-carbon double bond system. So CH3, 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 12 alpha hydrogens. Next C double bond system, 3 plus 3 plus 3, 9 alpha hydrogens.
9.
First is more
10.
stable. Yes, more number of alpha hydrogens, more is the stability. Next example, you try to compare between these three. Isobutylene, transbutylene, cisbutylene. What is the number of alpha hydrogens first?
6.
What is the number of alpha hydrogens? First compound. This is C double bond system. 3 plus 3, 6 alpha hydrogens. Second and third compounds, C double bond system. This is alpha carbon, this is alpha carbon, 6 alpha hydrogens. The third compound is also having
3 alpha hydrogen.
this is a butene, right? This is CH3, let us take. CH3, C double bond C, CH3. Okay, 6 alpha hydrogen.
6 alpha hydrogen.
Okay, isobutylene, transbutylene, cisbutylene. So CH3, C double bond C, CH3 in the cis fashion. So number of alpha hydrogens are same. So how to compare stability now?
By taking the position of CH3 and like trans
Okay,
is the
cis
most
and trans
stable.
compare. When cis and trans are compared, I can say trans is stable when compared to cis, because in trans we have minimum repulsions because the methyl groups are opposite. What about isobutylene and transbutylene?
Only 3 alpha hydrogen is available at a time for transbutylene.
Okay,
Both 6 alpha hydrogens are at the same side of the carbon.
okay. Like why you are looking at this particular carbon only? If you can say 6 alpha hydrogens are there only on this particular carbon, that automatically means the other carbon has no hydrogens. With respect to that perspective, I can say trans should be more stable. At a time, here also 6 alpha hydrogens are available, but on different carbon atoms. That's it. So it should be more stable means you have to write the hyperconjugated structures. So CH3, C double bond C, CH3. CH3 I am writing as CH2H, and we have CH2. This is nothing but your isobutylene. CH3, C double bond C double bond CH2, CH3. This CH electron density comes into this carbon-carbon pi electron density moves away. You will get CH3, C double bond CH2. Here we have H plus, no bond resonance, and here we have CH2 minus. In the trans, you try to write down CH3, C double bond C. I am writing this as CH2H, CH, CH3, CH. This CH electron density comes into carbon-carbon pi electron density moves away. So we'll be getting CH2, H plus, CH2 double bond C, CH bond as it is. This carbon will get negative charge, CH3 and CH. So when you try to write the hyperconjugative resonating structure for the isobutylene, what type of carbon ion you are resulting in? It is a primary carbanion. If you try to write the hyperconjugative structure in the trans-butene, what type of carbanion you are resulting in? It is a
Secondary.
secondary carbanion, which is more stable.
Primary. is
Primary
stable.
carbanion is more
Primary
stable.
Primary.
Isobutylene is going to be more stable. So whenever you have equal number of hyperconjugated structures, and if the two structures are cis and trans, based on repulsion, you have to compare. If both are not cis and trans, you have to write the respective hyperconjugated structures. If you try to draw the hyperconjugated structures, you will get idea like which carbon is obtained and which is more stable. Okay. So isobutylene greater, then trans to butene, then cis to butene. That is the right order. Compare here stability of alkenes A, B, C, D, E. 5 alkenes have been given to you. You have to give the right order. All of you try to give the answer, students. Can anyone give the answer for this question? Count the number of alpha hydrogens. How many alpha hydrogens are there in compound A?
10
Alpha
alpha.
carbon,
10 alpha hydrogens.
10 alpha hydrogen. Second one,
6 alpha hydrogen.
alpha. This is alpha. This is also alpha. 6 alpha hydrogen. 2 plus 1 plus 3, 6 alpha hydrogen. Third one, alpha
3
and
alpha
alpha.
hydrogen.
3.
Fourth one, D. Fifth one, E. How many in E? 4 alpha
4
hydrogen with respect to each C double bond C. But in E, in a D, can I say there is resonance?
No,
Conjugation
sir.
is there or not? No. What, Fatima? No.
Yes.
What?
Resonance is
Carbon double bonds alternate are there? No. So I can say in D, the
Yes.
resonance is there. In
Sir,
A,
but
B,
this site
C,
is vacant, na sir? Without double
which,
bond.
which side is vacant? No.
I
With
mean,
respect
there
to
is
these two double bonds, we have no. I'm not saying complete
yeah.
conjugation. I'm not saying
Then
complete
it's
conjugation.
present.
We can have so resonance is always given high priority. So D should be most stable. Because of D, because of resonance or mesomeric effect, D should be more stable. A, B, C, and E, they don't have resonance, they only have hyperconjugation. So just you compare A, B, C, E with respect to number of alpha hydrogens. After D, you have A. After A, you have B. Then you have E. Then you have C. So whenever you have resonance, that will be given the high priority. After that, you have to look at the number of hyperconjugated structures based on number of alpha hydrogens. So this is the right order. Yes or no? So we got that D, A, B, E, C, right? So resonance is there in compound E. In all other compounds, there is no resonance. I'm not saying complete conjugation, just two alternate double bonds are there. Next comes the concept of heat of hydrogenation. What is the heat of hydrogenation? Amount of heat released during complete hydrogenation of 1 mole of unsaturated hydrocarbon in the presence of metal catalyst. That means amount of heat released, how much amount of heat is going to be released during complete hydrogenation, that means addition of hydrogen of 1 mole of unsaturated hydrocarbon. If you take 1 mole of unsaturated hydrocarbon and you try to add H2 and you have to convert that to alkane, in that process, how much amount of energy is released? That is nothing but your heat of hydrogenation. So generally, heat of hydrogenation is directly proportional to number of pi bonds, because more number of pi bonds are there, more amount of energy is released. See, alkanes and alkane stability, you compare alkene and alkane. Alkanes are more stable. Yes or no? Like I have two types of alkenes, alkene 1, alkene 2, and I have both the alkenes are generating same alkane. So let us say alkane is having a stability and alkane has some stability, means it has some 100 units of energy, let us say. 100 units of energy is possessed by every molecule will have energy, every system. This water bottle also has some energy or not? This is stable, but every stable system also has energy. So this alkane is stable, so that has some energy. Internal energy of that alkane system, let us say 100 units. This alkene is unstable when compared to alkane, so it should have more energy or less energy?
More energy.
More energy.
More
Let us say alkene 1 has 120 units of energy. This alkane is same 100 units. Alkene 2 has even more energy, let us say 140 units. So alkene 1 and alkene 2 stability you compare. Alkene 1 is more stable when
Than
compared to alkene 2. Now you try to think of the scenario when alkene 1 is converted to alkane, how much energy is released? 20 units.
20.
Yes or no? Delta H will be how much?
Minus 20 units.
Minus 20 units. Here how much energy is released?
Minus
No,
40.
40.
Minus 40 units.
Minus
Understand
40.
the scenario now. When you are producing the respective alkane from unstable alkene, heat of hydrogenation will be high or low?
High.
high.
Heat of hydrogenation and stability of alkene, they are inversely proportional. So if alkene is stable, like alkene 1 you have taken, stable alkene if I consider, heat of hydrogenation is low. Unstable alkene 2 you have considered, heat of hydrogenation is high. Understood now? That is, heat of hydrogenation is inversely proportional to stability. Inversely, because if alkene is already stable, it will be converted to alkane and less amount of energy is released. If alkene is unstable, it will convert to alkane and more amount of energy is released. So stable alkene will be releasing out less energy. So heat of hydrogenation is inversely proportional to stability of alkene. This is the rule you have to apply. Stability of alkene. This is the rule you have to apply when the number of double bonds are same. When the number of double bonds are different, heat of hydrogenation is directly proportional to number of pi bonds, that is double bonds. If pi bonds are same, you have to look at stability of alkene. Compare heat of hydrogenation in these two cases, A and B. Compare heat of hydrogenation.
B greater than A.
B greater than A. First you have to check out number of double bonds. Greater the number of double bonds, greater will be the heat of hydrogenation. Then you have to look at, if the number of pi bonds are same, then you have to look at stability. So more number of pi bonds where we have in the compound A. So compare order A greater than B. Got it now? First you have to compare
Yes.
number
Yes,
of pi
sir.
bonds. If pi bonds are same, then only you have to look at stability of alkene. So heat of hydrogen is directly proportional to number of pi bonds. Compare order A greater than B. Compare here. Now we have same pi bonds. A and B have both the 2 pi bonds are there. Which alkene is more stable?
B, because the resonance.
Because of resonance, B is more stable. So heat of hydrogen is inversely proportional to stability. So which alkane is unstable? For that, more heat of hydrogenation. So absence of resonance in A, while resonance is present in B. So more stable alkene. So heat of hydrogenation will be more for A. Less stable, more. Less stable. Less stable means more heat of hydrogenation. More heat of hydrogenation. Right? So that is how you can compare the heat of hydrogenation in the two compounds A and B. Then comes the heat of combustion, students. Yes or no? The heading is still hydrogenation. Change it to heat of combustion. HOC. What is heat of combustion? What is heat of hydrogenation? When an alkene has been completely undergone, that is addition of hydrogen to that particular alkene has been done, or alkane has been done, and ultimately alkanes are formed. It is not like alkyne is converting into alkene, means that is not a heat of hydrogenation, because complete hydrogenation not occurred. 1 mole of unsaturated system should undergo complete hydrogenation. In that case, how much amount of energy is released? That is nothing but your heat of hydrogenation. Whenever you're talking of heat of combustion, the amount of heat released when 1 mole of given compound is completely burnt in the presence of excess of O2. 1 mole of hydrocarbon has to be completely burnt in the presence of excess of O2. In that case, you will be CH4 plus 2O2 gives rise to what? CO2 plus CO2 plus 2H2O. You can write down the equation in this fashion. CH4 gaseous plus 2 moles of O2 gaseous gives rise to CO2 gas plus H2O, 2H2O liquids. So delta H will be less than 0. So generally, heat of combustion is directly proportional to number of carbon atoms, that is inversely proportional to stability. Heat of hydrogenation, when you are talking about heat of hydrogenation, is directly proportional to number of pi bonds. If the number of pi bonds are same, then you have to look at stability. Heat of hydrogenation is inversely proportional to stability. Same thing here, heat of combustion, you have to look at number of carbon atoms. If a more number of carbon atoms are there, the carbon-carbon bond cleavages requires energy. In that case, more amount of energy is going to be released. So more the number of carbon atoms, more will be the heat of combustion. And if heat of combustion is same, that is, if number of carbon atoms is same, then you have to look at stability. If number of carbon atoms are there, heat of combustion is inversely proportional to stability. Compare here ABCD, which will have more heat of combustion.
D.
A.
Just now I have told you, no, number of carbon atoms you have to check
A,
out.
B, C, D.
A, B, C, D will be the right order. Heat of combustion is directly proportional to number of carbon atoms. Greater the number of carbon atoms, greater will be the heat of combustion. So A greater than B, B greater than C, C greater than D. Compare here A, B, C, D. First look at number of carbon atoms. A has how many carbons? 4 carbons. B has 4 carbons. C has 3 carbons. D has 2 carbons. So I can say A comma B set. A comma B set will be having greater. Then you have C, and then you should have D. How to compare between A and B? Which is more stable?
Trans is more.
Which is more stable? A is more stable. B is more stable. That is, trans is more stable. If a trans is more stable, it will have lesser. So A will be greater than B. A, B, C, D. That will be respective order for heat of combustion, right? So then you have studied 3 effects, students. The permanent 3 effects are inductive effect, hyperconjugation, and resonating effect or mesomeric effect. Whatever the stability, like different carbocations, when I can compare carbanions, free radicals, different compounds you are going to give. We look at the stabilities of now. Stabilities of those systems. Stability of carbocation. Carbocation has positive charge. Whatever the species which is decreasing the charge, that is increasing stability. Plus M, plus H, plus I, all of them decrease charge because they are electron releasing. In that case, whenever you have plus M, plus H, and plus I, in that case, charge is decreased, so stability increase. If you have minus M, minus H, minus I, in that case, electrons are withdrawn. Yes or no? Electron donating group, electron withdrawing group, electron donating group increases stability because decreasing charge. Electron withdrawing group decreases stability because it increasing charge. So with respect to this, we'll study a lot of examples now. Try to compare stability of carbocation here. CH3, CH2 plus, CH211, CH, CH2 plus, CH211, CH, CH plus, CH3. We have to apply all the effects now. Earlier we have compared the carbocation stabilities based on inductive effect only. Rather, after that we have seen stabilities of carbocations based on hyperconjugation only. Now apply every effect. I have given 3 species to you because
C greater
it is not
than
like,
D greater than.
yeah, it is not like only one effect is operative. Yeah, why reason? In A,
Due
what do
to
we have?
M and
In A, what type of effect we have?
hyperconjugation.
Plus H, very good. In B, we have resonance.
Resonance.
In C, we have resonance and
Resonance and
Hyperconjugation.
hyperconjugation. So because of resonance and hyperconjugation, C is more stable than B and then A. Right, very good. C, B, A, because resonance and 3 alpha hydrogens, resonance present, 3 alpha hydrogens present. Compare here. Stability of carbocation. Easy one, very easy.
C, B,
A,
A.
B, C.
C.
Yeah, A, B, C.
CBA.
CBA, why? Number of resonating structures differ.
Yes.
In compound A, we have 2 resonating structures. Compound B will be having more.
3.
Like we can
5.
write adjacent double bond also 3 resonating structure. Then you have 5 resonating structure. Greater the number of resonating structure, greater will be stability. So C, B, A. C greater than B, then A. This is the right order. Compare here PH3 C plus, PH2 CH plus, PH CH2 plus. Same here also.
ABC.
ABC because 3 phenyl groups are there. So with respect to 3 phenyl groups, positive charge in resonance. So number of resonance structures are decreasing from left to right. So A greater than B greater than C, that's the right order. More number of resonating structure. Okay. More structures. More number of resonating structure. Less number of resonating structure, RS. Compare here. ABC, 3 compounds have given to you. In A, do we have resonance?
Yes.
A has resonance, B has resonance, C do not have resonance. But among A and B, which is differing? Hyperconjugation is present in B, but not in A. A also has resonance. If you try to draw the resonating structure, the pi electron moves in this fashion, and you will get double bond CH2 positive charge here. B also has resonance. Pi electron can move. You get double bond between here CH2 and a positive charge. C no resonance, only hyperconjugation. How many hyperconjugated structures? If it is a positive charge here, then it should have CH3. If a positive charge on CH2, then it should be plus. If it is CH3, positive charge is actually present, CH2 plus. So this is alpha, only one hydrogen, so one alpha hydrogen. In this case, you have resonance and also resonance is there and also alpha hydrogens are there. How many? 3 plus 2. Resonance and 5 alpha hydrogens. Here you have resonance. So it should be more stable. B should be more stable, then it should be A, and then it should be C. B, A, C. Okay, this is CH2 with a positive charge on carbon, not on this particular carbon. Got it, structure? Got it, students, everyone? These structures?
Yes, sir.
Yes, sir.
Try to compare here. Stability of carbocation.
ABC.
Structure A, we have no resonance, only hyperconjugation is there. 7 alpha hydrogens, 3 alpha hydrogens, and 1 alpha hydrogens. So A greater than B greater than C, that will be the order of stability. This is alpha, 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 this is your respective alpha. So based on the number of alpha carbons, you can find out the number of alpha hydrogens. Greater the number of alpha hydrogens, greater will be stability. Compare here. CH2 C double bond H, CH2 plus CH2 C double bond H.
A. More stable.
Why?
Resonance. No, sir. B more stable.
B is more stable than AC.
B is more stable.
Because if you look at CH2 plus C double bond O, yes or no? So only minus I effect of CHO, no resonance. Because you cannot move the pi electron density in the opposite direction where you will be getting positive charge on oxygen. But if you look at second structure, you have 2 alpha hydrogens, so hyperconjugated structures. So you'll have B more stability when compared to A. Everyone got it or not? Here only
Yes.
minus I effect, no resonance. Here you have 2 alpha hydrogens, hyperconjugation is there. 2 alpha hydrogens means hyperconjugation present. Compare here.
CBA.
CBA. Shima says, yes or no?
Yes, sir.
Everyone got the same answer, any different answers? Anyone have different answer?
BCA.
Why? Why, Nandana? Okay, I'll give the
Sir,
hint. Yeah, please.
Sir, resonance is possible in B and C, but hyperconjugation is also there in B. That's why I thought BCA.
Okay. All of you think on structure B. Structure C. Think on structure C. What is it? More number of resonating structures, fine. Any other property it has?
It is anti-aromatic.
Yes, very good. Anti-aromatic in nature. So that anti-aromaticity has to be taken into account. So 4 alpha hydrogens in A, 2 resonating structures and 2 alpha hydrogens in B. In C, we have more number of resonating structures, but it is anti-aromatic in nature. C is anti-aromatic. Anti-aromatic always destabilizes. So B will be more stable than A. Then least stable is going to be C. Very good. Understood now? You have to think of aromaticity, anti-aromaticity also. Whenever there is an anti-aromatic structures, then because of anti-aromatic nature, that will be highly unstable. So B greater than A, then A greater than C. Try to compare this example I have given in the last class. If you remember, troponium ion and benzyl carbocation, which is more stable?
Troponium.
Why? Because troponium is actually having resonance and anti-aromatic nature with the involvement of positive charge. Whereas in benzyl carbocation, we have normal resonating structures. So compound A, aromatic due to carbocation involved in resonance. Because carbocation involved in resonance, it is gaining aromatic nature. In B, we have normal resonance of the carbocation. So A should be greater stable when compared to B. Different examples I'm explaining so that you don't get confused whenever you're solving questions. Stability order A greater than B. Try to compare here A, B, C. CH2, O, CH3, CH2 plus, CH double bond, CH2, CH3, CH, CH3.
ABC.
Why? Why A is more stable?
Complete octet.
Complete octet, very good. So whenever you try to draw the resonating structure, lone pair of electrons on oxygen comes into. We have CH2 double bond oxygen with one lone pair and a positive charge on oxygen, and CH3 is like a back bonding also, because oxygen is giving its lone pair to form a double bond with the carbon. So around oxygen you have 8 electrons, around this carbon you have 8 electrons, around this carbon also you have 8 electrons. So complete octet is present in all the atoms. So it will be having more stability. CH2 plus CH double bond CH2, CH3, CH plus CH3. Here you have incomplete octet for this atom, 6 electrons. Here also incomplete octet. Here we have resonance. Here we have hyperconjugation. So when you try to compare B and C, B is stable when compared to C. When you try to compare A, in the resonating structure, you have complete octet for all the atoms. So A greater than B greater than C, that's the right order. Complete octet due to resonance and hyperconjugation, A greater than B greater than C, that will be the right order of stability. Is that clear, students, everyone?
Yes, sir.
Yes, sir.
Yes. Then stability of benzyl carbocation. Mesomeric effect is observed on ortho and para positions only. And mesomeric effect at ortho and para is equal because it is distance independent. Mesomeric effect at meta position will be 0. There is no mesomeric effect at meta position. Only inductive will be operating at meta position. Try to compare now. Stability of benzyl carbocations and its derivatives. CH2 plus NO2, C6H4 CH2 plus OH, C6H4 CH2 plus Cl, simply benzyl carbocation.
C greater than D, then greater than B, and then A least stable.
So in A, what are the effects we have? Minus M is there.
Minus M.
In B, plus M is there. In C,
Plus M.
in C, minus
Plus M.
I. Inductive effect is dominant for halogens.
Sir,
Yes or
but
no?
there are more than 3 carbons in between them, right?
Yes, in that case, what happens? For halogen, inductive effect is dominant or not? If you go with the NO2, OH and halogens inductive effect is dominant when compared to mesomeric. So minus I you have to consider for chlorine. So we have CH2 everywhere. CH2 plus CH2 plus. So minus M effect is withdrawing the electron density, thereby increasing the charge, thereby making it destable. OH is actually donating the electron density, thereby reducing the charge and making it more stable. Cl is also withdrawing the electron density. So which will withdraw the electron density greatly? So NO2 will withdraw the electron density greatly. B is the donation, electron donation is happening only with B. So B should be more. A and C, they are electron withdrawing. So they should be less when compared to D, because in D there is no withdrawing. So after B you should have D. After D, with withdraw the electron density less. Chlorine withdraws the electron density by inductive effect, but NO2 withdraws the electron density by resonance. So withdrawing of electron density is highest in A. So A is going to be least. So B, D, C, A. This is the right order. Understood now, everyone?
Sir, why
Yes.
aren't we considering minus I effect of OH?
Minus
Like
I
we have
effect of OH is there. Minus I effect of NO2 is also there. But which is dominant? That effect has been written here. The dominant effect for OH is plus M effect, not the minus I effect. The dominant effect in NO2 is minus M effect, not the minus I effect. Okay. The dominance is electron donation with respect to OH, not the electron withdrawing by inductive. The dominance in NO2 is electron withdrawing by resonance, not the electron withdrawing by inductive. The dominant effect of chlorine is electron withdrawing by inductive, not the resonance, because of presence of lone pair of electrons, not plus M. Okay.
Okay, sir.
So the dominant effect is going to be deciding the ultimate stability, right? There may be other factors which are not dominant. They are not going to decide the final stability. Compare here. CH2NH2, CH2OH, CH2OCH3, CH2NH, C double bond to CH3. All are electron donating only. NH2 lone pair of electrons nitrogen, OH lone pair of electrons on oxygen, OCH3 lone pair of electrons on oxygen, NH double bond to
ABCD.
CH3. So I can say D is least because lone pair of electrons on nitrogen in resonance in both sides. D is least. Compare ABC. A should be having highest electron donation because lone pair of electrons on nitrogen are present and nitrogen is less electronegative, so donation is more. B and C, you have to think of bond angle concept again. So based on that bond angle concept, oxygen in OCH3 is more electronegative when compared to oxygen in OH. So B is going to be more electron donation than C than D. A, B, C, D, that's the right order. All of them has plus M effect. Plus M effect of given group decreases from left to right based on electronegative difference because of difference in electronegativity. Compare here. ABCD, compare the stability of resonating structures. Sorry. Compare here, students, all of you. ABCD, 4 structures have been given to you. You have to compare the stability of the respective resonating structures. Use the structure, right or wrong? Okay, fine.
D greater C, then B, then A.
Why, Faizan?
Sir, because if we consider resonance, their plus charge would be on para position, and
Okay.
thereby methyl groups will donate plus I effect.
Any other ideas? So I'm just trying to write the resonating structures. So we have double bond CH2 here and a positive charge will be able to ortho. For the resonating structure, you'll get a positive charge at para. So if you look at, I'm taking this particular resonating structure because everywhere you have para substitution. Now think of a structure, double bond CH2, and here we have a positive charge. That positively charged carbon is actually connected to CH3, which has 3 hydrogens. So these 3 hydrogens will involve in the hyperconjugation or not? It is like a positive charge carbon, carbocation carbon involving in the respect to hyperconjugation. So how many alpha hydrogens are there? It's alpha, sp3 hybridized carbon, alpha. So 3 alpha hydrogens. If you go with structure B, you have 3 alpha in structure A, 2 alpha H, in structure B, 1 alpha hydrogen in structure C, 0 alpha hydrogen in structure D. So where you will be having more resonating structure, that is more hyperconjugative structures in structure A. Yes or no? So A will be having more number of hyperconjugative
Greater
than
than
B
D, greater than C, greater than D.
greater than D, right? So we have to look at hyperconjugation also whenever it comes into picture. So 3 alpha hydrogens, 2 alpha hydrogens, 1 alpha hydrogen and 0 alpha hydrogen. You will get confused if you simply write alpha hydrogen, because you have to write the resonating structure. With respect to resonating structure, you have positive charged para. Because you have positive charged para, with respect to this positive charged para, these are alpha carbons. So these are alpha carbons, and you can count the number of alpha hydrogens. Okay, don't look at the inductive effect and 3 methyls are there, more electron donation. No, that will be leading to wrong answers. So stability order A greater than B greater than C greater than D, that will be the correct order of stability. Next is stability of anion. Up to now we have discussed different types of cations, benzylic carbocations and normal systems as well. Discuss the stability of anions now. Anions means what? They have negative charge. So we have two cases: electron donating group. We can also have electron withdrawing group. Electron withdrawing group decreases stability, decreases charge and increases stability. Decreases charge and increases stability. Whenever we have negative charge, that is anion is there, and we have electron withdrawing group, the charge is decreased and thereby stability is increased. Electron donating group increases charge and decreases stability. So what are electron donating group? It can be electron donation by plus M or plus H or plus I. Electron withdrawing can be minus M, minus H, minus I. So minus M, minus H, minus I groups, they will increase the stability. Plus M, plus H, plus I, they will decrease the stability. Generally, size or electronegativity, that is dominant when compared to resonance. After that, you have effects. Electronegativity or size, that will be dominant. Negative on more electronegative atom is more stable across a period. Negative on bigger size atom is more stable down the group. These points you have to understand carefully. You can understand the first point: negative charge on more electronegative atom is more stable. Second point is size. Negative on bigger size is more stable down the group. Why?
Due to less electron repulsion.
Yes or no?
Probably.
Due to less electron repulsions, negative charge on bigger size is going to be more stable. And the negative charge on more electronegative, obviously it has to be more stable. So this is what I have explained. Stability is directly proportional to minus M, minus H, minus I, stability increases. Plus M, plus H, plus I, stability decreases. With these logics, we'll study different examples now. Compare here, stability of anion.
A greater than B greater than C.
Reason, more number of resonating structures, can I say? So in compound A, we'll have negative charge coming into pi electron and moving away, 5 resonating structure. In B, you have 2 resonating structures. In C, CH3, CH2 minus. What do we have? Do we have hyperconjugation in C?
No, sir.
Because carbon ions do not have hyperconjugation. CH3, CH2 minus, no hyperconjugation. It is electron donating group, that is plus I effect only. No hyperconjugation. So A greater than B greater than C, no resonance, no hyperconjugation. A greater than B greater than C. Compare here order. CH3, CH2 minus, CH2 double bond CH minus, CH triple bond C minus.
C greater than B greater than A.
Because electronegativity dominating factor. So more electronegative, because sp hybridized carbon is having electronegativity of 3.25. It is a more electronegative even when compared to your nitrogen. sp2 hybridized will be having something around 2.75. sp3 hybridized will have 2.5. So C greater than B, B greater than A, that is the right order of the stability of anions. C greater than B, B greater than C, that will be the right order of stability of the respective anions. sp3 carbon, then you have sp2 carbon, then you have sp hybridized carbon. Electronegativity of carbon increased from left to right. So stability order will be C greater than B greater than A. More electronegative atom possessing negative charge is more stable. Is everything clear, students, so far?
Yes, sir.
Yes, right. Compare here CH2 minus CH double bond O, CH3 CH2 minus NO2. Stability of anion you compare.
ACB.
So minus M. C will be more or not minus M. N double bond O. The negative charge NO2 if you try to write CH2 minus N double bond O minus. If you try to write the negative charge into the N double bond O will now become NO minus. So C will be having greater minus M group than A. NO2 is a very strong electron withdrawing group by mesomeric effect. Then you have CHO. In B you have CH3. So C, A, B, that will the right order. Minus M effect order. Minus M of NO2 is greater when compared to minus M of CHO. Compare these two. A and B. A has resonance.
B.
A or B, which is more stable?
B.
Why?
Electronegativity and size as dominant.
Yeah, electronegativity and size, they are dominant when compared to resonance. Resonance is dominant when compared to effects like hyperconjugation inductive. So B will be having negative charge on sp hybridized carbon. So sp hybridized carbon having negative charge is more stable. So B should be having more stability when compared to A. So you should not compare the number of resonating structures and all. Number of resonating structures you have to compare only when the same type of carbon is having negative charge. That is same hybridization carbon. If the difference in the electronegativity is there, so then order of stability has to be decided based on electronegative difference. Phenoxide and carboxylate ion. This is a famous example. I think you all might be knowing this. Phenoxide ion and carboxylate ion.
Carboxylate ion is more stable.
Why?
B greater.
Why? Reasons.
Because negative charge remains on oxygen itself, which is more electronegative.
Yes, negative charge comes into pi electron is to move away. So we have CO minus C double bond O. So first point, why? Although carboxylate has only two resonating structures, carboxylate ion has two equivalent resonating structure. Ion has two equivalent resonating structure, and a negative charge is present on more electronegative atom. More electronegative atom in both the structures. More electronegative oxygen atom in both structures. Negative charge is present on more electronegative atom, more electronegative oxygen atom in both structures. Although you have 5 resonating structures in phenoxide, 5 resonating structures are there in phenoxide ion, but carboxylate ion is more stable. That is why carboxylic acids are stronger acids when compared to phenols. Phenoxide ion resonating structure, if you try to draw negative charge, you will get an oxygen. Negative charge you will get an carbon also. But if you look at B, carboxylate ion, equivalent resonating structures and negative charge on more electronegative oxygen atom. So stability order will be B greater than A. So that is why we always say phenols and carboxylic acid. If you try to compare, carboxylic acids are going to be more acidic when compared to phenols. And that is why carboxylic acid can also react with NaHCO3, whereas phenols cannot react. Right, students, let us proceed further. Stability of carbon free radicals next. Different free radicals we look at. Generally, electronegativity is more dominant than resonance. Then you will have effects, hyperconjugation and inductive effect. Stability is directly proportional to hyperconjugation. More number of hyperconjugated structures, more is the stability, and a plus A effect. Electron donating groups also increase stability. And a C dot, like carbon free radical on saturated, is more stable when compared to carbon free radical on unsaturated system, because in the unsaturated system, the carbon-carbon double bond already there. Because of the carbon-carbon double bond, what is having pi electron density is going to repel the odd electron, and that is why you will have carbon saturated dot will be greater when compared to carbon unsaturated dot free radicals. Compare here stability of carbon free radical. Compare the stability of carbon free radicals like ABC. In A and B you have resonance, in C you have hyperconjugation. In A, you have resonance and hyperconjugation. In B, only resonance. Yes or no? In A, we have, because this pi electron density is in resonance, pi free radical conjugation, pi free radical conjugation. So A and B have resonance, 2 resonating structures and 5 alpha hydrogens. This is alpha, this is also alpha. Here we have 2 resonating structures. Here you have 1, 2, 3, 3 is 9 alpha hydrogens. So based on that, what you can say? A greater than B greater than C. A greater than B greater than C. Is that clear?
Yes, sir.
Try to compare here. Stability of carbon free radical. More number of resonating structures in A, then less number of resonating structures in B, then 9 alpha hydrogens, then you have 6 alpha hydrogens, 2 resonating structures, 5 resonating structures. I can simply say A greater than B greater than C greater than D. A greater than B greater than C greater than D. So this is the correct order. Because more number of resonating structures in A, then you have less number of resonating structures in B. A and B at least have resonance, but C and D do not have resonance. C and D only have hyperconjugation. So A greater than B, B greater than C, C greater than D. That is the right order of stability of respect to carbon free radicals. Next comes the concept, students, bond dissociation energy. Like if we have a CH bond, if I try to break the CH bond, I'll generate a free radical or not? If I have an alkane, in that alkane I have a CH bond and I am trying to break the CH bond. CH bonds are not having great electronegative difference. So the bond cleavage in CH bond will be happening homolytically. Homolytic cleavage will lead to the formation of free radicals. So which bond can be easily broken? If the free radical obtained is more stable, then the bond can be easily broken. If a CH bond is there and I am trying to break the CH bond, generating a free radical, if the stability of free radical is greater, then the bond can be easily cleaven. If the bond can be easily broken, the bond energy is less. Yes or no? So bond dissociation energy you can understand like this. It is the energy required to break a bond homolytically. Bond dissociation energy is inversely proportional to stability of free radical. More stable free radical means weaker bond, the bond can be broken easily. Try to compare CH bond dissociation energy here. So if this CH bond breaks, you will get CH3, CH2 dot. If this CH bond breaks, you will get CH3, C, CH3, CH3 dot. So it has 9 alpha hydrogens, it has 3 alpha hydrogens. Which is more stable? This 9 alpha hydrogen is more stable. If it is more stable, the E2 can be broken. The CH bond in the compound B can be broken easily. So A has more bond dissociation energy when compared to B. Bond dissociation energy order. Bond dissociation energy. Bond dissociation energy order is A greater than B, because in A, if the bond has to be cleaved, you will generate a less stable species. But B, if the bond is cleaved, you will generate a more stable species. Same logics. So in A and B, if you try to cleave the bond, you will be generating CH3, CH2 dot and CH3, C dot, CH3. So stability order will be B greater than A. Bond dissociation order will be A greater than B, because they are inversely related. Is that clear, students?
Yes.
Yes, right, very good. Then acidic strength. Acids are substances which donate the H plus ion. I can say acid is going to be more stronger acid when the conjugate base is more stable or not? Yes or no? If we are
Yes, sir.
getting the H plus ion at a conjugate base, if the conjugate base is more stable, that means the H plus ion is obtained fastly, because the bond cleavage happens at a greater rate. If that is happening greatly, then you can say more stable the respective conjugate base is. If the conjugate base is more stable, then what you can say, the respective acid is a stronger acid. Stronger the acid means higher the value of Ka. Higher the value of Ka means lower the value of pKa, because pKa is negative logarithm of Ka. Let's look at those perspectives. Ka is equal to concentration of H plus into concentration of A minus divided by concentration of Ha. Ka greater means pKa lower. Ka greater means more acidic. More acidic means concentration of H plus high. So pH will be less. Everything will be opposite with respect to weak acid. For weak acid, concentration of H plus will be less, Ka will be less, pK and pH, they are going to be more. pK and pH, they are going to be more. Understood, right? Acidic strength is directly proportional to stability of conjugate base or the anion. So based on this logics, we are going to compare now. Compare the acidic strength here. This is a very interesting example. Compare acidic strength here. So you'll be generating what? First example, you will be generating phenoxide ion. Second, water you have, you will generate H plus and OH minus ion. Third, you will get RO minus ion.
C greater than B greater than A.
C greater. C alcohol and phenol. What
A
poison?
greater than C.
Phenols are more acidic, right? Because phenoxide is more resonance stabilized. In C, we don't have resonance stabilized for RO minus. In B, OH minus is not resonance stabilized. So A is going to give, upon loss of H plus, A gives phenoxide ion, which is resonance stabilized or not. So A will be highest. That we can compare. Now compare between B and C. Don't need to worry. Okay, if you are getting wrong answer, that's a good sign. You are learning something new. Which way you should not think that you have learned. A is greater. B and C you have to compare now. How to compare among B and C?
So inductive effect.
Yeah, Nandana, inductive effect. You apply inductive effect, what you will get?
B and then C because CH3 is electron releasing, so it will be unstable.
Okay, A greater than B greater than C. Okay, that will be right order. So A greater than B greater than C. So phenols are going to be more acidic than water. When compared to water and alcohols are going to be least acidic. Now we have studied one concept of bond angle. Like OH and OR, which oxygen is more electronegative? OH and OR.
OR.
OR oxygen is more electronegative. That OR oxygen more electronegative means what? The more electronegative
stable.
oxygen from OR, possessing negative charge should be more stable. So OR minus should be more stable or not? If you consider bond angle concept.
Yes, sir.
That should not be considered. Why? Because we have another group as hydrogen. Instead of hydrogen, if you have any other group, if we have R, O, PH here, then you have to compare negative, then you have to compare obviously more electronegative oxygen is OR oxygen because of bond angle concept. But whenever you have hydrogen, you should not consider bond angle concept. You have to take the electron donating tendency of inductive effect. That has to be dominating factor, and OR minus is less stable. Got it now? If you
Yes, sir.
if you compare OR, electron donation tendency, the electron donation tendency of OCH3 is less if it is connected to phenyl group, because the oxygen of OCH3 is more electronegative. But if you compare the same with respect to ROH, you are saying RO minus is more stable. RO minus is less stable because R is actually electron donating. Whenever you are comparing the acidic strength of alcohols and water, you have to look at electron donation tendency because R group and H groups are connected. Bond angle is not the dominant factor because repulsions are less because of hydrogen. Okay. So RO minus means plus I effect of alkyl group. Why this is interesting means because if you consider bond angle concept, you will get C greater than B, not B greater than C. So phenols are more acidic than water, then alcohols are least acidic. Compare here. ROH, CH triple bond CH, NH3 CH4.
A greater than B greater than C.
A, B, C.
Why? I have repeatedly
Because
said many times that sp hybridized carbon has an electronegativity of 3.25. The sp hybridized carbon is more electronegative when compared to nitrogen also. So here we get RO minus, here you get CH triple bond C minus, here you get NH2 minus, here you get CH3 minus. Negative charge of more electronegative is more stable. Most electronegative is oxygen. Then you have sp hybridized carbon, then you have nitrogen, and then you will be having carbon. So A greater than, B greater than, C greater than D, that will be the right order. Try to solve other example. Everyone got this or not?
Yes.
yes,
Try to solve this. CH3 C double bond OH produces CH3 C double bond O minus. Phenol produces respect to phenoxide in this fashion. compare acetate and phenoxide, which is more acidic, which is more stable. Comparing acidic strength means I'm comparing the stability of respective conjugate base. Acetate ion is produced when acetic acid undergo loss of cleavage of OH bond. Phenoxide ion is produced whenever phenol undergo loss of or cleavage of OH bond. Just now we have seen in acetate ion we have two equivalent resonating structures and negative charges. Negative charge is present on more electronegative oxygen. Because of that, acetate ion is more stable. If acetate ion is more stable, acetic acid is a stronger acid. Equivalent resonating structure, whereas in phenoxide we have non-equivalent resonating structure. Based on that, all of you, we can compare the respective stabilities, and you can say non-equivalent resonating structure is less stable when compared to equivalent. So A greater than B. Try to compare here. You take this as homework, all of you. Okay, you take this as homework. And since this is the last session of 2022, and since tomorrow we don't have any class, I just want to wish all of you a very happy advanced new year. And I
Advance
wish
Happy
all
New
your
Year.
Happy New Year, sir.
Thank you, sir.
Happy
Happy
New
New Year.
Thank you, sir.
thank you everyone.
Thank you, sir.
And I wish all of your dreams come true. You will be going to the best universities of your dream. Okay,
Thank you so
all
much.
your
sir.
hard work will be coming true. And in this New Year time, since it is not a virtual, since it is not an offline session, I just want to ask one question. So although it may be something different, try to answer one question which is interesting, which I found interesting. So if you consider any matter, like we consider ourselves human beings or any other matter, they are made of what ultimately, atoms or not? Like if you consider human bodies, they are made of biomolecules like sugars, carbohydrates, proteins, nucleic acids, DNA, RNA, all that. And those biomolecules will consider of different monomeric units. Those monomeric units will consider some different types of atoms. Those atoms will consider subatomic particles. That is how the chain goes. So we are made of biomolecules. So we have some mass. Biomolecules have some mass. So we are made of some biomolecules which are having mass. Biomolecules are made of monomers. Monomers have mass. So biomolecules will also have mass. Monomers are made of atoms. Atoms have mass. So the monomers will also have mass. Atoms are made of subatomic particles. Subatomic particles have mass. So the atoms are also having mass. But what is the subatomic particles made of? Everyone understands the question, right? Subatomic particles are made of what species such that they have mass? Do they have some other particles which have mass? This is a very interesting question. You try to think on it. Okay. So happy New Year once again, all of you. Thank you all. Have a great day. Bye.
Thank you, sir.
Thank you.
Thank you, sir.